Hi everyone, I am Saniya Kuller and this is cute little Yang Shi. And today we're going to be talking about conditional independence. If you're given a joint probability table, are two random variables independent given a third random variable? That's what sort of we're going to be talking about today. So here, using our example with A, B, and C random variables, we will learn the A's, the B's, and the C's of conditional independence in this long and detailed video. So let's get started, little guy. He's all pumped up. So I'm with cute little Yangshi here. Yay, peekaboo. And if you're watching this video, then that means you want to get a very detailed, solid understanding about conditional independence and work through a lot of the examples to really hone in and practice those skills and get more clarification. So this is my longer video. I do have a lot of other videos on my YouTube channel regarding probability, Bayes rule, other calculations, other tools, and tips and advice. So please do subscribe and check those out. But if after watching this you still have some more questions, please do reach out. And if you want a quick version of conditional independence, I do have a shorter version on YouTube as well. And all the links are here in the bio, so please do check those out. But in this video, we're going to go through a worked example of conditional independence. I'm going to go through all the calculations as well and go a little bit beyond what I do in the shorter video, along with showing a little bit more of the concepts and behind the scenes. Make sure that you understand what's going on. So this is a longer video, so we'll be taking more of our time here, but I do have a shorter video on conditional independence. So please do check that out. And again, I'm Saniya Kuller and I'm really happy to help you guys. And he is too. Aww. He's nodding. So please note that the question then is, given random variable C, are random variables A and B, are they independent? So A and B independent of each other given C. So the formula that we'll be using is to see if the probability of A and B given C is the equal to the probability of A given C multiplied by the probability of B given C for all values of A, B, and C. So this is sort of what this represents. So we're not sure if these edges should be there. But if indeed random variable C, given that it occurs, if it makes A and B be independent of each other, like in this situation here, if there's no more uncertainty, if the probability of A and B given C equals the probability of A given C multiplied by the probability of B given C, so if A and B are independent given random variable C, that's what this represents here, then this is sort of like a Bayesian network. And in this case, this would be like a common cause, where each of these directed edges is a conditional dependence. I do have other videos talking about this, but we were going to talk in this video how to see whether or not A and B are independent of each other given C. And independence is given by this upside down T sign. So A and B are independent given C in this diagram. But we're going to see how we can test if this is the case. Please do subscribe for more updates. So again, I'm Saniya Kuller and this is cute little Yangshi. And this is an example of a Bayesian network with a common cause where A and B both come from their parent C here. So in conditional independence, what I want you guys to see is another example. So here, let Y be a project due, X be a news group that is busy, and Z be a lab that's full. So if we have a project due, then the news group could be busy and the lab could be full. That's a common cause. So the common cause for the news group being busy and the lab being full would be the project being due. So is the news group busy and the lab being full? Are those independent of each other? No. But instead, they are conditionally, these two are conditionally independent given Y. So the news group being busy and the lab being full are conditionally independent given the fact that there's a project due. So the project being due, is why we observe this relationship between news group being busy and the lab being full. So once we condition on the project being due, then any relationship we see between this X and the Z goes. Whereas here, instead, this is a common effect where both of these are like the parents for this one little child, traffic. So X is raining and Z is ball game, and then Y is traffic. So if it's raining and then there's a ball game, then we could observe traffic. So are X and Z independent? Yes. So raining is very different, is independent from the ball game, right? I mean, I don't, in this example, they are not connected, right? But maybe if it was raining, then we might observe that there couldn't be a ball game. But imagine that it's like a professional ball game, right? The tickets are sold, right? If it's raining and there's a ball game, those are two independent events. But so they are independent, but are they conditionally independent given Y? So are they conditionally independent given traffic? No. This is for a common effect. But here we're focusing, our example is trying to see if this is like a common cause, because a common cause may not have, the first one is called, what we're checking here, this is mainly marginal independence, but we're testing for conditional independence. And then this is what conditional independence looks like often as a common cause. And indeed, conditional independence. So in probability theory, two random events, A and B, are conditionally independent given a third event, C. Probability of A and B given C, right? They are conditionally independent if the occurrence of A and the occurrence of B are independent events in their conditional probability distribution given C. So in other words, A and B are conditionally independent given C if and only if, so this is what this means. So if and only if, given knowledge that C occurs, knowledge of whether A, if and only if, given knowledge that C occurs, if we know that C occurs here, knowledge of whether A occurs provides no information on the likelihood of B occurring. So let's say we know that C occurs. So if we know that A occurs, it does not give us any more knowledge about the probability of B occurring. And knowledge of whether B occurs provides no information on the likelihood of A occurring. So if A occurs, we still don't know much about the probability about B. Still unknown. It's still unknown. But similarly, in the same vein, we can also say that, for the C here, if C occurs and B occurs given that, it does not give us much information about A occurring. So in the standard notation of probability theory, A and B are conditionally independent given C if and only if the probability of A and B given C equals the probability of A given C multiplied by the probability of B given C. So conditional independence of A and B is denoted by A with this upside down T B given C. So this is the formula here. And we're going to try to test this across 8 cases and a joint probability distribution table to see if indeed it's the case that A and B are conditionally independent given C. That's what we're going to test here in this video. And this is a longer version of the video. So this is just another example here of a common cause. X is causing Y and Z. So here, based on this network, we can say that Y. So based on this network, we can say that Y and Z are independent given X. So Y is independent of Z given X. So knowing X, knowledge about X, makes Y and Z independent. And what we see, the relationship between Y and Z sort of disappears once we condition on X. So what this means is the probability of Y and Z given X is just equal to the probability of Y given X multiplied by the probability of Z given X for all values of X, Y, and Z. So this is conditional independence. But this is not conditional independence because in this situation, X goes to Y, X goes to Z, as well. But the thing that we've done is we've added a link here. We didn't have a link between these two. We've added a link between y and z. So y is not independent of z given x. So y and z are not independent given x. So knowing x does not make y and z independent. So basically, the probability of y and z given x is not equal to the probability of y given x multiplied by the probability of z given x. So this one here is basically no conditional independence. While this one is independence. Yay! So this is an example again of conditional independence here. That's what it's shown by here, independence given something. And this is no conditional independence. Mm. So conditional independence, as we've seen, could be like common causes. So common causes or ancestors can also give rise to conditional independence, like cancer. This could be cancer. Cancer is leading you to get x-rays, and dyspnea as well. So basically the probability of C given A and B is just equal to the probability of C given B here. Essentially what we can see based on this common cause is that A and C are independent given B. So again, in this example, what this is just saying is that A is independent of C given B. Since A is independent of C given B, then the probability of C given A and B is just equal to the probability of C given B. And similarly, what we can say is that the probability of A given C and B is equals the probability of A given B. That's all we can say too. Then we can say here that the probability of A given C and B is just equal to the probability of A given B. So the probability of A given B is the same thing as the probability of A given C and B in the situation. It doesn't matter whether C occurs. B occurs. Knowing whether or not C occurs does not impact the probability of A occurring. It's just the probability of A given B. So similarly, the probability of C here given A and B is just the same thing as the probability of C given B. It does not matter whether A has occurred or not. It's like we could slash this part out. It does not make a difference. And this again is showing that cancer is a common cause of the two symptoms, a positive X-ray and dyspnea. I have dyspnea C because of cancer B, so I do not need an X-ray test A. So this is just another example of conditional independence. Another example of conditional independence here, so we can see this other network with age, gender, smoking, cancer. So we can say that cancer is independent of age and gender given smoking. Cancer given age, gender, smoking is equal to the probability of cancer given smoking. Because it is conditionally independent of age and gender here, so it's independent of age and gender here, it's almost like those don't even matter, because cancer is independent of age and gender given smoking. So cancer is independent of age and gender given smoking. It's a direct parent here. So given smoking here, cancer will be conditionally independent of age and gender. So we can say that cancer is independent of age and gender given smoking. So essentially cancer given age, gender, and smoking is just the same thing as probability of cancer given smoking. Knowing about age and gender does not really influence what we observe for cancer. What really matters when determining the probability of cancer given smoking, it does not matter whether age or gender, what those are in particular. It just matters what smoking is. So these parts don't even make a difference. That's why we could just cut these parts out. Essentially, we can just cut these out here. We can just cut these out here because cancer is independent of age and gender given smoking. So now we're going to talk about the problem that I'm going to work with you guys through in this video. And again, I have a shorter video where I go through this a little bit more quickly, but here we're going to take our time to go through this example here. So this is what we'll be working on in this video. And then we'll be going a little bit beyond to understand conditional independence a bit more. So please bear with me. So I think that there are 8 random outcomes here. So what we're finding here is that A, B, and C are Boolean random variables. So they each have 2 outcomes, true or false, true or false, true or false for C. So I think a Boolean like boo, liar, what you say is false. So A, B, and C each have 8 total outcomes, 2 by 2 by 2, which is 8. So we're going to be going through those outcomes to figure out, if A and B are independent of each other given C. Given this joint probability table, is A independent of B given C? So there are 8 outcomes over here because, A, B, and C are Booleans, boo, liar, they can have true or false values. They can be false or true. And so we have these 8 outcomes here and their respective probabilities. And you can sort of think of probability in the following way. So I love chocolates. You can't have them, little guy. They're not healthy for you to have. But I'm not a huge dark chocolate fan. I really like the milk chocolate. So what is the probability that I'm going to get a peppermint bark one instead of the dark chocolate, just the peppermint bark light chocolate chocolate one, given that I really like it over the other one? So it's like that. So let's see. Probability is all about like drawing things sometimes. So what is the probability out of all of these here? Now let me try. Completely just trying to pull out one. And he's a pretty curious cat. He's trying to see what I will end up drawing out. Oh. I got dark chocolate. Actually, it's healthier for me. And what's the probability he's gonna get this sweet? Like the same one, it's all the same. So he's gonna get the same one. So I'll give it to you, Yankee. 1 second. And also this little me who's comfort too. Hi, me. And you also get it, Yankee. Here. 1 second. You want it? Okay, if you don't want it, just leave it right here for you. If you want it, you can have it here. But anyways, so we want to know, given this joint probability table, is the variable, random variable A, is it independent of B? Given that we know the value of C. That's sort of it. And I have other videos kind of talking about all the things we can do with this joint probability table. Because in the end, we sort of have all the 8 possible outcomes of A, B, and C and the corresponding probabilities that all sum up to 1 here. Is A independent of B given C? So the given C part is just referred to this part, given C, given C, given C, given C, and this is the same given C. So is A independent of B given C? So typically, you can just think of this as just saying given C. We're just tacking this on here. We're just tacking on the given C here. Because if A and B are independent, then what we would say is that if A is independent of B, then the probability of A and B is just the probability of A multiplied by the probability of B. So now all we're saying is A independent of B given the value of C? So all we have to do is to each of these probabilities, we just need to add the given C part. So we take the same idea here that you see here, and all we're going to do is just add the given C, which is just this part here, the given C, which is this, which is this, which is this, which is this here. This is what we need to find. So probability of A and B given C, which is what this is saying here, if it's equal to the probability of A given C multiplied by the probability of B given C, then A is independent of B given C. That essentially is how you calculate this conditional independence. So please note that if A and B are conditionally independent given C, so A and B conditionally independent given C, like a common cause, this is what it would look like. C as a common cause for A and B such that A is conditionally independent of B given C, what we notice here. And similarly, that means that the probability of A given C is the same thing as the probability of A given C and B have occurred. And similarly, the probability of B given C is the same thing as the probability of B given C and A. So if that is the case there. So those are the probabilities that are here as well. And to determine conditional independence, this would be the formula. Probability of A and B given C is just the probability of A given C multiplied by the probability of B given C. That's what this is here. So we're seeing if this is the case, or if instead A and B are not conditionally independent given C. That is, A is not independent of B given C. And this is an example of why this could be the case. There could be an arrow pointing from A to B, or maybe there could be an arrow pointing from B to A, or so there could be anything like this, for instance. We don't know right now, but we could do more tests to figure this out here. We could have a link going back in this direction here. And basically that just means that the probability of A and B given C is not equal to the probability of A given C multiplied by the probability of B given C. That there are some values of A, B, and C for which this does not hold. So we're going to try to test this using our joint probability distribution table in our example. And a heads up is that, we actually are going to conclude this here. But again, we are not too sure what the final network would look like here, how we would represent it, but it could look something like, C pointing to A and B, and then B pointing to A, or something like that in general. It just is that it wouldn't look like this. That's what we can tell. So what we're going to use is we're going to use B's rule, Yangshi, and I have videos going through this. So as we just have seen that if A is independent of B given C, then probability of A and B given C is equal to probability of A given C multiplied by the probability of B given C for all the possible outcomes of A and B. So we need to use this, and this has to be true for all the outcomes. So this here is the probability, this part here, probability of A given C, and this part here is here. Oh gosh. So essentially what you're going to see is that probability of A given C is a probability of A given C essentially. This bar means given. So probability of A given C is the probability of A and C divided by the probability of C, while PB given C is the probability of B given C, which is just PB and C divided by PC, the probability of C happening, the event. And again, these values can be true or false, so it really depends, and we're going to talk about this more. So don't worry, I'm going to explain everything because I'm that person too. I need to see everything step by step sometimes. So I want to be that kind of teacher to you guys. And so probability of A and B given C equals probability of A given C multiplied by probability of B given C if A is independent of B given C. So again, adding in the given C means that we add in this given C here, this given C here, and this given C here. So each part we add that on. And as we just saw from Bayes' rule right now, these are the same here, and these are the same here. So basically what we can just see, in other words, is that, if A is independent of B given C, then, probability of A and B given C is just equal to this probability. So Another way is the probability of A and C multiplied by the probability of B and C divided by the probability of C. That's all that it is. So essentially, in the second step, we need to find the probabilities that we need from the joint probability table. So from that formula, we need to calculate the probability of A and C, the probability of B and C, and the probability of C. It's all just a matter of speak. Or as cute little Yankee would say, it's all just a matter of meow. Meows, I don't know if they're the same or not, but it's just a matter of speak overall. So if we wanted to see if A and B were independent, then the probability of A and B is equal to the probability of A multiplied by the probability of B for all possible values of A and B. So because they're Boolean random variables and they're basically like events, A and B, they could be true or false. Like Boo liar, they could be true or false here. So basically, A could be false and B false, A false and B true, C true and C and B false, or both of them could be true. So we need to consider all four of these possible outcomes for A and B and test all four of them. And if even one of these tests fails, then A and B would not be independent. So sometimes when you're doing these tests and you're calculating it by hand, to see if A and B are independent, calculating out this formula, then it can take a while to show, okay, testing that both are false, if this holds, testing if A is false, if B is true, like, testing one by one by one. But if one of these fails, then you can just say that A and B are not independent, and then you can be done. So sometimes you might even just want A and B to not be independent. So because you might just be spared from testing all of these out. But I like numbers. I like having to do these calculations. That's why I like majored in math and took up a lot of courses in math as well, because I don't mind this. I find it kind of nice. But you might just find it very tedious to go through all of these. And I'm going to just enumerate what all of these are. So if we want to test this out, for all four values, so if A is false and B is false, then the probability that both of them are false here, if we need to see if it equals the probability that A is false multiplied by the probability B is false. So basically we're taking this equation and we're putting in the specific values of A and B in there and seeing if the equation holds for all four of these possibilities. So like for instance here, so for A is false and B is true, we need to test that the probability that A is false and B is true is equal to the probability that A is false multiplied by the probability B is true. And then here, the probability that A is true and B is false needs to equal probability A is true multiplied by probability B is false. And lastly, the probability A is true and B is true need to equal the probabilities A is true multiplied by the probability B is true. So if A and B are truly independent, all four of these conditions, they need to be true. If even one again fails, like if we find, for instance, that this is not true, then we have to say, A and B are actually not independent. So so we have to test all of them, and that's what I meant, that sometimes you can just be spared all of them. Or maybe maybe all of these are true till you go to the last one, and then you find that they're not independent anyways, but you had to do all the math. So it is what it is. But again, yeah, all four of these need to be true. So yeah, this is just listing out like all four of these statements that need to be true. Like that means that, this probability on the left needs to equal this multiplied probability on the right for all of these possibilities. And if all four of these are true, then A is independent of B, which again is the same thing as saying that B is independent of A. But if one of them fails, or more than one of them, or maybe all four of them, or two, just at least one of them needs to fail for A to not be independent of B, or the same thing as B not being independent of A. We can define two random variables as being independent in an unconditional model, and I have another video on this, so please do see this out, like our A and B independent as we'd seen, right? So this means and here, means and. That's what the caret means here. So A and B are independent if the probability of A and B equals the probability of A multiplied by the probability of B. And this is the unconditional model. This is when we just think of A and B being independent. However, in this video, we're talking about a conditional model, where the conditional is given essentially by the fact that we have, and what makes this conditional is the fact that we're given C here. So probability of A and B given C, if that is equal to the probability of A given C multiplied by the probability of B given C, then we can say that, A and B are independent of each other given C. That's what we get from the conditional model. And we can say as is. So A is independent of B given C. So this term right here, this thing right here means independent. This statement here, you could just say that A is independent of B. And from this one right here, we can see from the conditional model that A is independent of B given C. So again, this is what it means here. This caret or this pi upside down means that A is independent of B given C. So given C, A and B are independent of each other. And to test that out, we have to see if the probability of A and B given C again equals probability of A given C multiplied by the probability of B given C for all values of A, B, and C. And so if we're looking at A, B, and C, all values, then there are 8 total values that they can have. So what conditional independence essentially means here is that, like in this case, given C occurring, right? Like if we have knowledge about C taking place, so if we know that A occurs, so A given C, right? A occurs, it does not give us any information on how likely B is to occur. And similarly, so if we know that C occurs, if we know that B also occurs, given that C occurs, it does not give us any information on how likely A is to occur. So that's what's meant by conditional independence. So given the knowledge that C occurs, knowing that A occurs does not give any information on how likely B is to occur. And knowing that B occurs does not give any information on how likely A is to occur. So similarly, if we want to see if A and B are independent given C, then if you remember from before, the same equation is holding, except the fact that we're having, given C. What that would do is we just have to tack on this given C part here, given C here, given C. And then all the corresponding probabilities were the same, except that we're just tacking on this given C here, given C, 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 given C. Like that's all that's happening. So it's an independent test for seeing if A and B are independent given C. Thus, we really need all 4 of these statements to be true for A to be independent of B given C, which again is the same thing as saying that B is independent of A given C. So we need the probability that A is false and B is false given C to be equal to the probability A is false given C multiplied by the probability B is false given C as the first one. We also need the probability that A is false and B is true given C to be equal to the probability A is false given C multiplied by the probability that B is true given C. So the probability that A is true and B is false given C to be equal to the probability that A is true given C multiplied by the probability B is false given C. So it's all a conditional probability instead now. And lastly, the probability that both A and B are true given C to be equal to the probability that A is true given C multiplied by the probability that B is true given C. So it's just same idea, except now we're also just conditioning on C, because now we know that C is true. We have that information and we should use this information. As a Boolean random variable, however, we need to go a little bit deeper because since C is a Boolean random variable, it's essentially an event, it can have these two possible outcomes. C can be true or it can be false. So as you see here, I've just said given C here. But we know what C is. We know C could be either true or false. So we need to now consider being a little bit more specific. So I just showed you how we can take the same idea and just tack on given C. So it's the four equations here that we had before, but we just tacked on the given C, just resulted in adding this bar, means given, and then the C here. But now we also need to consider and see, pun intended, the specific value of C, if it's true or if it's false. And that's why what we're going to see is that each of these is going to break apart into two possible equations that we need to test. So if we're given, the same thing can be have C being true or C being false. So the way that you can think about it is we have our C here now, and we can see our C, and C is for cat. Hi, Yankee. C, this little cat, can be true or it can be false. So true or false. And then, so like if C is true, we have our A, B over here. And again, we have the four sets of values that they can have. False, false, both false, false, A false, B true, A true, B false, or both true. And then we can see the same thing here for both of them. But like see, if A is true, then we have conditional probabilities that we observe for A and B. We have the probability that A is false and B is false, given that C is true here. A is false and B is true, given C is true. A is true and B is false, given that C is true. And A and B are both true, given that C is true here. So these are all given that C is true. So they're all conditioning on this over here. And we're determining them, and they could change these probabilities that we observe these events. They can change given that C is true. But if C is false, what we're going to notice is that instead these probabilities are defined, these same events of A and B being true or false or what the values are going to be given that C is false. So out of this situation when C is false, what are the probabilities that we observe the events that we observe? So they're going to then differ. But since this is a conditional probability, we have to condition. We know, given that a certain outcome, either C is true or false. So we have to be specific now. And now you can see, whereas before what we were essentially doing, we're just like ignoring, all of this stuff here. We weren't even considering, and even for the next table too, we just were not considering any of this part here. Not at all. We were not considering it, so we had just four unique outcomes, these four outcomes here. We did not consider, if we're just testing if A and B are independent, we did not consider B at all before. But now, since we're now looking given that C is true or false, we have these 8 possible outcomes. So for each situation for A and B, A is false and B is false. So A is, here, there, we need to consider, what if C is true? What if C is false? So for each set of all outcomes for C, we have these two possible outcomes here. So it's the idea that since we have 3 random variables now in the fray, A, B, and C, we have 8 outcomes to consider, whereas before we were just looking at A and B, we just had these 4 outcomes, but now we're conditioning on C. So if C is true or C is false, that's going to impact the probability that we observe that both are false, for instance, so that A is false and B is true, and so on. So we have these 8 outcomes. Then if C is true again, I just want to zoom in on this to help you guys. We know that C is true, we just start conditioning on that, and then we have the set of outcomes that we are going to use here for each of these 4. And we also have the same set of outcomes for A and B, but if we're conditioning on C being false, then these probabilities will get adjusted respectively. And so we're going to adapt our equations before based on what C is true or false. So now, going back to the original equation here, cute little Yangshi in the back. So we just need these statements to be true. So there were these 4 statements from before, and now we just need to understand that C can be true or false for each of these. And so we need to break them apart into the set of values of C. So basically for these 4, since we have 2 possible values of C, we're going to have the 8 total equations. So 8 total tests. So as I mentioned, it gets kind of tedious to do this. So basically, we need all 8 of these statements to be true for A to be independent of B given C, which is the same thing as B being independent of A given C. These are the 4 statements we were talking about before. So probability A is false and B is false given C equals probability A is false given C multiplied by probability B is false given C. So there are these 2 outcomes of C, C being true or C being false, and we need to condition on each of those. So again, you see 2 for each, when C is true and when C is false. So for each of these 4, we're considering C is true and C is false. C is true, C is false. C is true, C is false. So 2 outcomes for each of these 4 statements. Thus, we have those 8 outcomes there that we're seeing. So A is, what we're seeing here again is A is false and B is false here, given that C is false equals probability A is false, given that C is false, multiplied by the probability B is false, given that C is false here. But in this next example, probability A is false and B is true given C is equal to the probability A is false given C multiplied by the probability B is true given C. And we need to then consider those outcomes of C. So, what if C is true? Then we need to see if the probability A is false and B is true given that C is true equals the probability that A is false given C is true multiplied by the probability B is true given C is true. But then C could be false, and then all we have to do is we just have to change this value of C to being false then, which is what we do on the second part here. But we're seeing the probability A is false and B is true, given that C is instead false. Is that equal to the probability A is false given C is false multiplied by the probability B is true given that C is false? Then we're also testing this third statement, which is, A is true, probability of A is true and B is false given C. Is that equal to the probability that A is true given C multiplied by the probability B is false given C? And C could be true or false. So we need to consider those outcomes of C. C being true, 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 or C being false, false, and false. And lastly, we need to see if probability that, A and B are both true given C, if that's equal to the probability that A is true given C, multiplied by the probability B is true given C. So all we do is we add in, what if C is true? Then true here, and true here. We put in true here, here, and here. But if C is instead false, then we just put false here. False, false, and false. So there are these 8 outcomes that we have, which I've highlighted for you guys. Yay, highlighter. Now, so we really need to test that all 8 of these statements are true. So conditioning on C being true or false, we need to test 8 statements. That's why I was saying that sometimes if we're doing these Bayes rules, it may even be better that you find like at some point one of these is not true, and then you can just say A and B are A is not independent of B given C, which is the same thing as B is not independent of A given C. So if even one of these 8 fails, then you can say that A is not independent of B given C. So otherwise you need to test all 8 of these. And if all 8 of these are true, then A is independent of B given C. Otherwise, A is not independent of B given C. If even one fails, if at least one of these fails, then the A is not independent of B given C, which is the same thing as B not being independent of A given C. Otherwise, we have to test all 8 of these, Yangshi. That's a lot to test. And if all of these are equal, then A is independent of B given C. Thus, we need all 8 of these statements to be true for A to be independent of B given C, or equivalently, B is independent of A given C. So these are the 8 same statements, and because we are not sure yet, I'm going to put a question mark over the equal sign because we're not sure. But we need to test that all 8 of these hold true. And if all 8 of them hold true, then A is independent of B given C. which is the same thing as saying that B is independent of A given C, as I was mentioning, it's just a matter of speak. But if one or more of these is false as you're checking along, then A is not independent of B given C. Then that's not the case, which is the same thing as saying that B is not independent of A given C. So sometimes this is better, as I was mentioning, because if this one or more of these being false, otherwise you're stuck going through all the calculations. But yes, it's pretty rigorous to show that A is independent of B given C, but it's just kind of like applying the math repeatedly. So please note that here I kind of switched up the order of the statements based on how I'll be going through them right now. So this is what referred to as 1, 2, 3, 4, 5, 6, 7, and 8. So these are the respective tests that we need to verify and validate. So I'm going to be going through them in this order. So then we need to obtain the probabilities from the joint probability table. So what we're going to first focus on is the probability of C values that we need, because as you can see, pun intended, that we do use C a lot. So we need to find the probability that C is true. So you can see from this joint probability table that I've sort of pieced it together, where I have the C values here and then the true and the false values here. And then to find the probability C is true, I just have to add all these respective values when C is true here, these four outcomes. So that's 0 plus 0.3 plus 0.2 plus 0.2, and that is 0.7. So the probability that C is true is 0.7. Then the probability that, so basically to verify, this is just 0.7 here. That is the probability that C is true. And the probability that C is false is just taken by outcomes when C is false. So we add the 0.3 plus 0 plus 0 plus 0. So that's 0.3 here. That's the probability that C is false. And we just have to add these numbers together and make sure that they add up to 1. So again, all these outcomes, 0.7 plus 0.3, they add up to 1. So that's great. So we have these probabilities to work with. So probability C is true is 70% and probability C is false is 30%. Hi, Tuggle. Oh, little Tuggle is saying hi. Hi, Tuggle. Hi, little guy. Aww. So if we want to find the probabilities where C is true, we sort of just have to focus on this joint probability table and just eliminate the situations when C is false, which are these last four rows. As you see here, C, pun intended, C is false here. So we're just focusing on the top, which is where C is true. And then we want to gather the probabilities that we need, which is the probability that A is true and C is true. Probability A is false and C is true. Probability B is true and C is true, and probability that B is false and C is true. That's what we want. And what you'll see here, when intended, is that if we're looking at the probability that A is true and C is true, so that part is just going to be A is true and C is true. So since all of these are true, essentially, we're just focusing on the values of A over here. So A is true and C is true. That's this part here. So this one will be given by 0.2 plus 0.2 here, which is 0.4. So these are, it doesn't matter if B is false or true. And I kind of explained this more in another video, how we do this. But it doesn't really matter what B is. We just care about A being true and C being true. And then here, if we are looking at A being false and C being true, instead we're focusing on these here. We're focusing on these rows here. That's what we're focusing on here, the top part. And then we're going to have 0 plus 0.3, which is just 0.3 here. So again, it doesn't matter if B is false or true here. But one of the steps, so you see that
Pun intended. So you're seeing here essentially that we have these four outcomes here that we have used. For A is true and C is true, we highlighted these two yellow ones here. That's what we highlighted here. And then for A is false and C is true, we have these orange here. Is that little orange cat toggle? So these should collectively sum up to the probability that C is true, because again, we didn't really care if B is false or true. We just care about A and C here. So if we add all of these up, which they should add up to the probability that C is true, which is just 0.7. You can see this visually as well because we used all four rows where C is true. And we found earlier the probability C is true is 0.7. But just to kind of show you as well, so if we add this plus this, essentially because A can be true or false, that means that for any value of A, essentially adding up on A crosses out, it just, it crosses out like A essentially because you're crossing it out because A is true or false and you're considering both. So what you have in the end is C is true, which is 0.4 plus 0.3, which is 0.7. So again, this is 0.4 plus 0.3, which is 0.7, which is indeed the probability C is true. And similarly, if we can focus on B instead. So what we can see here, yeah, I won't be annoying about the C part, but anyways, is that we can focus on probability B is true and C is true here. So C is always true because of what we have subsetted it here. So if B is true, this part here, this is just 0.3 plus 0.2. It doesn't matter here what A is. So the probability B is true and C is true is just this 0.3 here plus this 0.2 here, which is 0.5, 50% of the time. Again, we're controlling for any value of A, the false value, which is the 0.3 part, and when A is true, which gives us the 0.2 part. And then, lastly, we want to see when B is false and C is true, and again, A can be true or false. So then we have, for this part, we have the 0 plus 0.2, which is just 0.2 here. Because B is false and C is true, B is false, C is true, that's what this gives us. And again, if we verify that we add this 0.5 here, if we add this 0.5 and this 0.2 together, they equal 0.7, which is probability C is true. So right now you see it like this, but just for you to also just check that you've added them up correctly, because here, you just want to make sure, and you see that they add up to 70%, which is the probability that C is true. So that's great. So this added to 70%, this added to 70%, and these are just different slices, probabilities based on the variable that you're using, A or B, given that C is true. And then we can do the same analysis when C is false. So we can see that if A is true and C is false, what that is, all of these things when C is false. So we're just going to get rid of the part of the table. Now the other part, the top part, because now that's for C is true. We're focusing here instead on when C is false on this bottom half. So what we see here is the probability that A is true and C is false, and the probability A is false and C is false. So given C is false, we look at the both possible outcomes for A, the true and the false. So if we're looking at probability A is true and C is false, A is true and C is false, then we're going to have these values here. So ultimately what we will see here is that we're going to, pun intended, we will have the 0 plus the 0 here, which is just 0. That's what we get here. And similarly, if we're focused on A false and C false, then we just focus on the top part, which is A false, C false, A false, C false. And we get 0.3 plus 0, which is 0.3. And when we add those up together, these two probabilities up, essentially this is 0.3, which is the probability that C is false. So remember, this was 0.7 probability C is true, and then this was 30%, which is probability C is false. So this adds up to 30%, which is the probability that C is false, which is great. And it's again, like when you're doing this, because we're adding A is true plus C plus A is false, then essentially like we're just controlling for A both values. And it's just the same thing as probability C is false, because A can be true or false. So adding them up together essentially like negates us focusing on A. So similarly, we're also going to focus on B part of it. And we're going to see the probability that B is true and C is false. So B is true and B is true and C is false, and B is true and C is false. That's just going to be equal to 0 plus 0, which is 0. So that's what this becomes here, this probability, which is 0. And then the probability that B is false and C is false are going to be given here. And that is 0.3 plus 0, which is 0.3. So this should be a 0.3. So when we see this, then what we are observing is that, so this is 30% here, and this is 0, and this is this value here. This adds up to 30%, which is the probability that C is false. So these all work out for us. So again, this is 30%, and this is 0, this is 30%, and this is 0. So these are what the probabilities become. So just to summarize the probabilities that we've gathered so far, so we know the probability C is true is 70%, C is false is 30%, and these add up to 1 as we expect. We see that and this part here is 70%, and we are seeing that any time for C is true, the probabilities that we get, these should add up to 0.7, which is also like what this is. And any time, and similarly here too, these should also add up to 0.7, which they do. And we also see that, pun intended, that when A is true and C is false, these probabilities should add up to 0.3. And similarly, these two add up to 0.3 as well. So these are the probabilities that we have learned so far. So A is true and C is true is 40%, A is false and C is true is 30%. Aww. And B is true and C is true is 50%, B is false and C is true is 20%. These add up to 70%, and these add up to 70% here too. Hi, Toggle. And then probability A is true and C is false is 0. Probability A is false and C is false is 0.3. These add up to 0.3. And then probability B is true and C is false is 0. And then the probability that B is false and C is false is just 0.3. And these add up to 0.3, 30%. Now I have quite a little gang. I have Toggle. Toggle. Aww, there's a little Toggle here. Here's Toggle. Oh. And there's me. So I'll just show them 1 second. They're very, very cute. toggle. Hi. They're very cute. You can see them there. But anyways, they also want to eat, pun intended, they also want to learn about probability. Right, guys? Okay, so yes. So anyways, next what we want to do is we want to find the probabilities for A and B as well. So we want to find A being true and B being true. You know, remember there were 4 outcomes. Toggle, no. Okay, okay, he's still there. The 4 values, you know, A can be true, B can be true, A can be true, B can be false, A can be false, B can be false, and both um, of them can also be such that A is false and B is true, or both of them can be false here. So these are the 4 outcomes here. So what we're going to see here is that it's easier because we were sorting it on C being true or C being false. You can do it either way. So I just wanted to group them together based on A and B values falling together in these categories as well of like, so for like A and B, values could be like, this is like a truth table. I remember learning it in geometry class in high school. So the values could be like false and false, true and false, false and true, or just true and true. Well, there are many ways you could write this truth table here, but because I organized it, this is how it looks here. So now if we're looking for the probability A is true and B is true, so both are true, then we're going to just see that I've grouped them together, and the only key difference between these 2 rows is just the outcome of C. So C can be true or false. You know, true is and false is, so you know, it doesn't matter. So what we see here is that we're just going to take this 0.2 that we have here and this 0 and then just add them up to get 0.2. So that's how we get this value here, 0.2, 20%. And what we see, and so since these are all 4 possible outcomes for A and B, they should add up to 1 in the end. Like that is what they should add up to. They should add up to 1. So that's what we see here. And then now we want to see probability A is true and B is false. So A is true and B is false. So that will give this to us here. A is true and B is false. That'll be like 0.2 plus 0. So that's what we have here, which is 0.2. And then what we want to do is we want to see probability A is false and B is false. So both of them are false. So what we were going to do here is we're going to say, okay, both are false. So that's just the top one, false and false. You know, and you see that C can be true or false here. And that's what we get here, which is 0 plus 0.3, which is just 0.3. And last but not least, we see that the remaining unshaded parts here are for A is false and B is true, and C can be true or false. So that will be 0.3 plus 0, which is 0.3. And now if we add all of these up together, we have 0.2 plus 0.2, which is 0.4 plus 0.3, 0.7 plus 0.3 is 1. So this adds up to 1, which is great. Yay, we won! So please note all of the probabilities that we have gathered. So again, these are the ones that we had just gone through before, but these are the 4 that we talked about right now, you know, for A and B. So again, probability A is true and B is true is 0.2. Probability of A is true and B is false is 0.2 or 20%. Probability A is false and B is false is 30%. And lastly, probability A is false and B is true is 30%. So these are all the probabilities, and they're going to be very core to us solving and checking those 8 different equations. And along the way, if any of them fails, the equalities, then we can say that A is not independent of B given C, or vice versa, B is not independent of A given C. So if any of those 8 finish, but I'm just going to If that's the case, I'll just still go on and show you all 8 just for your reference. So that if you had to, how would you do it? That is, like, if you were given these probabilities and had to calculate them, how would you do it? That's why I want to go through all of them in case we find along the way that there's no independence. Then how would we do that? And that's what I'm going to try to do. That is, like, if you were given these probabilities and had to calculate them, how would you do it? That's why I want to go through all of them in case we find along the way that there's no independence. Then how would we do that? And that's what I'm going to try to do. So these are all the probabilities that we've gathered, as I mentioned, and they're going to be like a formula sheet as we are going through and essentially trying to check all these 8 different conditions here to see if these are true. And if all 8 hold true, then A is independent of B given C. And if one fails or more, then A is not independent of B given C. So we're going to get started by checking each of these. And again, because I want to show you how you would calculate all of these, I'm going to walk through all of the examples, but in reality, you just can stop at the first one that is false for you. If that's the case, otherwise it might turn out that all 8 are true, then A is independent of B given C.
So thus, please note that our input that we're going to be using is we have this set of probabilities that we have determined. And Yangxi's saying, yes, let's use it. Aww. He's agreeing, let's use this. We have this set of probabilities over here, and we have these 8 statements to check to see if these hold. And all 8 of these need to be true in order for A to be independent of B given C. So if all 8 are true, then that's the case. Otherwise, A is not independent of B given C. So we're going to use this data, and we're going to use these formulas here, and we're going to test this out.
So for this first test, we're going to see if the probability that A is true given that C is true multiplied by the probability B is true given that C is true, if that is equal or not to the probability A is true and B is true, that both of these are true given that C is true. So given Bayes' rule, this probability right here can just be expressed in this formula here. As we mentioned earlier, that's how it can be expressed. And then this other probability can be expressed in this way here. Okay. So that is the probability that A is true, given that C is true from Bayes' rule. Bayes' rule. Again, I have other videos talking about this too, some more. So from Bayes' rule, as we had derived, then this formula is probability A is true given that C is true is just equal to the probability A is true, and you slash down this part here. You always slash this down on the top, and C is true. So you slash it down and make this an and on the numerator, and then this part becomes the denominator. So it's the probability A is true and C is true divided by the probability that C is true. And we had calculated that probability A is true and C is true is 0.4. And we know that probability C is true is 70%. So this probability is 0.4 over 0.7. And similarly, so that's what this one becomes. So similarly, for this probability, we find the probability B is true given that C is true equals probability that B is true and C is true divided by the probability C is true, which is 0.5 over 0.7. So we have these probabilities here, and we're just going to multiply them. So that's what we're going to do. We're going to multiply, we're going to multiply these here, this part here, and also this part here. Okay, so I'll just maybe leave it with maybe an underline of purple. Okay, so then what we do is we just start multiplying them here. So this 0.4 over 0.7 becomes here, and then this 0.5 over 0.7 becomes over here, and we're just figuring out what the left-hand side is. And that is 0.2 over 0.49, which is approximately 0.408163. So this part right here, this is the left-hand side. This part here, all of this calculation right here was for the left side. It was for the left side, this left side here. And now we want to find this probability here on the right side, which is A is true and B is true given that C is true. So using Bayes' rule again, all we have to do is for the denominator typically is what, we're given that C is true. That's what the denominator is. And the numerator just takes this part that we're interested in, A and is true and B is true here, and it also slashes down this given and makes it an and. So it's just saying A is true and B is true and C is true. That's what the numerator is. So we found from before, from the joint probability table, that this is 0.2, and the probability that C is true is just going to be 0.7. So when we do this, we find that this is 0.285714. So this is the right-hand side. So what this value is this part is 0.285714, and this part right here is just going to be 0.408 So we definitely know that these are not equal to each other. So since probability A is true given C is true multiplied by probability B is true given that C is true, since it's not equal to this probability, A is true and B is true given that C is true, this shows that there is no independence here, that A and B are not independent given C. That is, A is not independent of B given C, and which is the same thing as B is not independent of A given C either. So in reality, I would have just been done with this, and I would just say, yay, this shows that there's no independence here. That A is not independent of B given C, or B is not independent of A given C. That's what we can conclude, and we don't have to do all those 7. So if that was like an assignment, I may not, but I might try to do a couple other like off the sheet just to verify that, just to make sure my math is all okay as well, or also for practice. But since I want to show all of them to you, I'm gonna kind of go through all of them. But you wouldn't really have to do that. As soon as you find one that's violating it, you're done. Otherwise, you have to go through all 8 and then see if that works out for you. If all of them work out, then there is independence. So we're going to go to the next one. Even though we kind of already know the answer, I just sort of want to show you the other probabilities just to show you how we can calculate it. So from this, we would be done. We would already be done with the problem. So you could just finish right here and be done. But I'm going to kind of walk you through the other steps and how you can solve them in case you started with those other probabilities.
Thus, you'll see that I found some examples where the conditional independence properties, they do not hold. I could have just stopped with this one example now that we found it, and that's what I do in this short video. Again, please see the bio, please do subscribe. I have a shorter video where we stop at the first example, but here I want to show you all the 8 tests so you could follow along and understand the concepts. But basically, we will already know that A and B are not conditionally independent given C. That much has been established now.
So while we could have stopped, right now, because we already found a situation that shows us that A is not independent of B given C, which again is the same thing as C saying B is not independent of A given C. But I just wanted to show you all the examples, to show you like all 8 of them, just in case, just so that we can go over the probability concepts. But in reality, just one example out of the 8 where it failed and you're done. So here next I want to show, yeah, these cute little guys are sleeping here, but like the probability that A is true given C is true multiplied by probability B is false given C is true. If that is equal, is it equal to probability A is true and B is false given that C is true? Let's see if that is the case. And again, if this doesn't work, if hypothetically, like we hadn't seen the other example, number one, which also didn't work, then, we would have said, then, that this is not. So now we definitely kind of are taking it from the mindset that it's definitely not independent, but I still, again, want to just go through them just so that you can understand if you're given just the completeness of solving the whole problem and how you would get those probabilities and do those checks if you were given that situation. I think reinforcement is a good thing. So the probability A is true given C is true, and working these out, guys, will help you guys get stronger in these concepts. That's equal to the probability that A is true and C is true divided by the probability C is true, which is 0.4 over 0.7. And again, this denominator here is 0.7. And the probability that B is false given C is true is, you just slash this down and say probability B is false and C is true divided by probability C is true. And this numerator is 0.2 divided by 0.7. So we looked at our formula sheet that we had gotten with all those formulas from, and then we just plug these in. So we do like kind of like the hard stuff first. And then we multiply these together here. As said over here, we multiply this 0.4 over 0.7 by 0.2 over 0.7, and we get 0.08 over 0.47, which is approximately 0.163265. That's what's on this side, the left side, 0.163265. And then we look at the right-hand side, which is the probability A is true and B is false, given that C is true. And what we get is, for the numerator again, we just say A is true and B is false and C is true. And the part where this given makes a difference is that this becomes the denominator, probability C is true. And we know from our previous work that the probability A is true and B is false and C is true is going to be 0.2 here. Then you divide that by 0.7, and then it is 0.285714. So thus, this left-hand side evaluated here to 0.136265, that's what this was, and the right-hand side evaluated to 0.285714, and they are not equal. So again, this would have been enough, like if we had just done this one, for instance, by itself, it would have been enough to say that there's no conditional independence here. So A is not independent of B given C, the same thing as saying that B is not independent of A given C. But again, I'm just trying to show all the results. So if you understand all these concepts so far, you don't have to watch the rest unless you want to see the working out of the other solutions, which I recommend. But this is sort of, now we go from, the question mark is now this, no. So they are not conditionally independent.
Okay.
Again, just powering through the third example is we're going to see probability A is false given C is true times probability B is false given C is true, if that's equal to the probability A is false and B is false given that C is true. So again, I'm just using different color coding schemes in case any of them happens to make more sense for you for these problems as I'm showing them to you. But basically, we're going to look at the left-hand side here, and we're going to evaluate the left-hand side. So probability A is false given C is true. That was 0.3 over 0.7. That was what we got from probability A is false and C is true divided by the probability C is true, 0.3 over 0.7. And then the probability B is false given C is true is equal to the probability B is false and C is true divided by the probability that C is true. And this is 0.2. When we multiply them together, then that equals to 0.06 over 0.49. So this is 0.12249. So that's what we get on the left-hand side when we evaluate this. This is what this is approximately equal to. And on the right-hand side, the probability A is false and B is false, given that C is true, is the probability A is false and B is false and C is true, divided by the probability that C is true. And all of this happening is 0. 0 over 0.7 is just 0. So what we see here is that on the left-hand side, we had 0.122449, and that is not equal to the right-hand side, which is 0. So therefore, since both sides are not equal, there is no conditional independence here. And again, this would have been enough by itself, but I just am showing all 8 of them, these results. So in the fourth example, now what we're going to do is we want to find the probability that A is false given C is true multiplied by probability B is true given that C is true, and see if that is equal to or not the probability that A is false and B is true given that C is true. So the first one here, so again, this is another color coding scheme. The first one that we're seeing here is so what we're seeing here is that for the probability A is false given that C is true, that is just probability A is false and C is true divided by the probability that C is true. So that's like 0.3 over 0.7 for this here. And then the probability B is true given C is true is probability that B is true and C is true divided by the probability that C is true. So that's like 0.2 over 0.7. So then this maps to this here, which is here, and this maps to this here, which is here. So you multiply them out, you have 0.06 divided by 0.49, so that's 0.122449. So that's what the left-hand side evaluates to. Then on the right-hand side, we're looking at the probability A is false and B is true, given that C is true. So what we're getting here is we're getting A is false and B is true and C is true divided by C is true, those probabilities, that's 0.3 over 0.7, which is approximately 0.428571. So the left-hand side evaluates to 0.122449, and the right-hand side evaluates to 0.428571, and they're not equal to each other. So again, this also just further shows that A is not independent of B given C. So there's so many ones here that did not end up being independent at all. So you might also be thinking, maybe that's just how things are, right? But I kind of want to show you that that's not always the case. We could have some examples where this does work out, where they could be equal to each other. So I want to also show you what that little victory looks like. So basically, in the fifth test, we're seeing if now we're conditioning on C being false, and so you'll notice that the denominator is changed to C being false, which we found was 0.330% instead of 0.7, because 0.7 was the probability C was true. So now here, I'm going to be seeing if the probability A is true given C is false multiplied by probability B is true given C is false, if that is equal to or not the probability that A is true and B is true given that C is false. So here what we will get is that A is true and C is false divided by probability C is false. That is equal to 0 over 0.3, which is just 0. And then here, the probability that B is true and given that C is false is just equal to this. So B is true and C is false divided by C being false, the probability, which is 0 over 0.3, which is 0. So 0 times 0 is 0 here. This is just 0. And on the right side, the probability A is true and B is true given C is false. This evaluates to probability A is true and B is true and C is false in the numerator, divided by the probability C is false in the denominator. So that's just 0 over 0.3, which is just 0. So what we're noticing is on the right-hand side, this just evaluated to 0, all the way to 0. And on the right-hand side, this also just evaluated to 0. So that's, this probability is the same thing as this side. The left side is the same as the right side. So since 0 is 0, this test has passed. So this is just an example of what the success looks like when, because you might be thinking, hey, like all four so far have not been working out, they've not been independent. So far, like, I mean, that independence test has not been passed with the first four. So just kind of want to show you what success looks like. And if you got example like this, then you would keep on going typically till you found one failure. And again, I'm trying to enumerate all 8 of them for you guys. I would have stopped right at the first one, the way it lucked out. But what if I started off with this example? That's what I kind of want to show you guys. Like, maybe you started off with this example and this works for you, so you'd have to keep working through the other examples then. So this test has passed here, but and I would have kept on going to the next one that I have on my list. And that's what I would have done. But since 0 equals 0, this test has passed. But I already know from before that, the first 4 tests were not equal. So I already kind of am going into it knowing that A is not independent of B given C. It's the same thing as saying A is not independent of B given C. Since the first 4 tests, I just needed at least one of them to fail. But this is just an example of what success looks like. But we remember we needed all 8 tests to be equal. We needed get rid of the question mark here, that it is equal. So this is an example of equality when the left-hand side equals the right-hand side, when that is true. And if all 8 of those statements that we were going through were true, like this is an example of them being true, then we would have said that A is independent of B given C. I just wanted to show this to you. And for the 6th test, we are looking at the probability A is true given C is false times probability B is false given C is false, and seeing if that's equal to the probability that A is true, B is false, and B is false given that C is false. So to evaluate this again, so we're going to look at, the probability A is true given C is false. And that's A probability A is true and C is false over the probability that C is false, which is 0 over 0.3, which is 0. This just crosses out to being 0. Then we look at the probability that B is false, given that C is false. And that would just be equal to the probability B is false and C is false, which is 0.3, divided by the probability C is false, which is 0.3. So this is just 1. So we multiply this 0 here by 1 here, and that just becomes a flat 0. So the left-hand side is thus 0. And for the right-hand side, what we see here is that we have the probability of A is true and B is false, given that C is false, is equal to probability A is true and B is false and C is false, divided by the probability that C is false. And this is 0 over 0.3, which is just 0. So the left-hand side is 0, as we saw here, and the right-hand side is also 0. So since 0 equals 0, this test passed. And again, we already know that A is not independent of B given C, but this is just another example of a test that passed, which is nice, just for you guys to see. What we're going to see here is the probability that A is false, given that C is false. Oh. Wow. So that was actually pretty cute. Wow. Okay, wow, that's very emotionally attached. Yeah, it's very cute. So I just had to record that. So there's very cute cats, Ming and Yang Sheep. So here we're going to look at the probability A is false given C is false multiplied by the probability B is false given that C is false. And we're going to see if that's equal to the probability that A is false and B is false given that C is false. So for this one here, for the seventh, that we're almost at the end, guys. Here's the probability A is false given that C is false, which is equal to the probability A is false and C is false divided by the probability that C is false, which is just 0.3 over 0.3, which is 1. So because when ever like A is false and B is false and C is false, that is 0.3. So, A is false and B is false would definitely be 0.3 here as well, which is what they were here. So the probability B is false given that C is false is the probability B is false and C is false divided by the probability C is false. So that's 0.3 over 0.3, which is 1. So then the probability that A is false given C is false multiplied by the probability of B is false given C is false is 1 times 1, which is 1. And then so the right hand side, we also have to evaluate, and we also get 0.3 over 0.3, which is 1. So left hand side is 1, and the right hand side is also 1. So 1 equals 1. So this test passed. So the seventh test passed. But again, we already know that A is not independent of B because the first 4 tests, and you'll see that whenever in this situation, when C is true, the first 4 tests that we did, the test did not carry out. But we're going to see as well in this 8th and last example here that when A is false and B is true, so we're going to be looking at that. So probability A is false given that C is false multiplied by the probability B is true given C is false. Is that equal to or not the probability A is false and B is true given that C is false? That's what we're going to see. And so we're looking at the probability that A is false given that C is false, which is just the probability A is false and C is false divided by the probability C is false. So again, the numerator is always going to be this part, whatever, however much there is on this part, and whatever is on this part. So everything is just connected with an and then this part here always goes in the denominator. So that's 0.3 over 0.3, which is 1. And then probability B is true given C is false is the probability B is true and C is false divided by the probability C is false. So that's 0 over 0.3, which is 0. So when we multiply these together, we have 1, which is what this is, multiplied by 0, so that's 0. And on the right-hand side, probability A is false and B is true, given that C is false, is the probability A is false and B is true and C is false divided by the probability that C is false. So that is just 0. The numerator is 0 divided by 0.3, which is 0. So since the left-hand side here is just, this part is all 0, and the right-hand side is also just 0, then we know that this test passed. But again, for the 8th and final test, we know that A is not independent of B given C. And we can tell this because when we needed all 8 of these statements to be true for A to be independent of B given C. So what we see here from all these 4 that we were going through respectively, the first 4, whenever C happened to be true, they all ended up not being the case. And it was just how things worked out in this situation. But in the last 4, when C is false, then those were true. But the key idea is that we needed all 8 of these to be true in order for A to be independent of B given C. But since at least 1, and in this situation, in this problem, 4 out of the 8 were false. So remember, we just needed 1 to not be true for this to not work out. So, that's what we had. 4. We have like 4 of these. A is not independent of B given C. We had 4. So thus we conclude that A is not independent of B given C, which is the same thing as saying that B is not independent of A given C. And again, guys, we could have stopped a long time ago when we were checking, in this case, the first situation, where we saw this. We could have said that the first statement fails and we're done. But I wanted to show you guys how we just work with Bayes' rule and finding these additional probabilities as well. And I'll have a shorter version where I'm just kind of walking through the first example and then showing, yep, we're done. But like, what if that didn't work out for you guys? I just and you started off like, let's say with C is false, then you'd have to kind of go through all of many of them, you know, at least 4 or 5 of them. So I just wanted to show that to you guys. If I asked the question, given this joint probability table, is A independent of B? Given C, the answer is no. A is not independent of B given C. There is at least one situation where that is not the case for one set of values of A, B, and C. But in fact, we found 4 such situations, and those usually center around C being false in a situation, as you can see. Thus, given this joint probability table and the calculations that I just showed you for those 8 tests, A is not independent of B given C, which is equivalent as saying that B is not independent of A given C, since one or more of the 8 tests that we had failed. So that's how you can find conditional independence.
Please note that in our example here, what we will see is that A and B are not independent given C. So we do not see conditional independence. But I want to show you what would happen if indeed A and B were conditionally independent given C. Like if the 2 random variables were conditionally independent, what are some of the things that we could kind of learn from that, or what that would mean? So let's hypothetically pretend that A and B are conditionally independent given C, and I want to show you what all we can learn from that here. So kind of looking ahead, like let's say hypothetically that we had found that A is independent of B given C. So again, the independence term here is given by this. So if it was indeed the case, this is the independence. So if it was indeed the case that A is independent of B given C, then for all 8 possibilities, like, and we had, in this video, I've shown all 8 of us of testing all 8 statements, because there are 8 total combinations for 3 random Boolean variables. So if probability of A and B given C equals probability of A given C times probability of B given C, for all 8 possibilities, then we could say that A is independent of B given C. And then based on that, we can actually derive these 2 additional probabilities. So the probability of A given B and C would just be equal to the probability of A given C. And similarly, the probability of B given A and C would just be equal to the probability of B given C. So a way to see that again is that let's have this as yellow for A, and here's A. And similarly, let's put this as green, is this, and here. So you can notice some connection, right? A given B and C, just A given C, B is like slashed out here in this part. Similarly, B given A and C is just probability of B given C. So I'll just show those and motivate those for you guys. If it was indeed the situation that A is independent of B given C, then I'm showing why we can say that the probability of B given A and C is just equal to the probability of B given C. So it's almost as if we don't need to know that A and C occurred. So again, what we mean here, the same thing, A is independent of B given C. So knowing that C happened, if A happens, it does not lead us to any more information on or impacting the likelihood of B occurring. And similarly, given that C occurred, if B occurred, it does not give us any more information about A occurring. So these are the probabilities here. So we can express this probability right here. We can express this guy right here using Bayes' rule. And using Bayes' rule, we see that the probability of B given A and C, the numerator would just be A, probability of A and B and C, and I talk about this in other videos, so please do see those, divided by the denominator is always what's right of this given, what we're conditioning on, probability of A and C, which is what this is here. So the numerator just kind of attaches all of this together in an AND statement, A and B and C, and the denominator is just A and C here. And then what we notice is that we can express the probability of A and B and C similarly using conditional probability. So probability of A and B and C can be written out again as probability of A and B given C multiplied by the probability of C. That's what this was written as here. And the denominator just stays the same, probability of A and C. Then in the next step, what we do is we focus in on this probability here. So we hone in on this probability, the probability of A and B given C as well. And what we write it as is we write it in the following way. So we say that the probability of A and B given C is, so essentially this part here, this probability here, a probability of A and B given C, is what we express here. Since A is independent of B given C, then probability of A and B given C is just equal to the probability of A given C multiplied by the probability of B given C. So that's what this part now becomes. So this part just becomes this part here. That's what it gets fleshed out into. And then we keep the probability of C here. And similarly, for probability of A and C, we can just express it this way as the probability of A given C multiplied by the probability of C. And this, guys, again, this is just Bayes' rule at work. That's what it was here too. It was also Bayes. The numerator was also Bayes. And the denominator is just the probability of A given C multiplied by the probability of C. Then we do some slashing and thrashing. We notice the probability of A given C is on the numerator and denominator. So we slash this part out here. That's what we do here. We just slash this part. And then probability of C in the numerator and the denominator. So slashing it out just gives probability of B given C. Thus, we can see that the probability of B given A and C is just the same thing as the probability of B given C. It's just and. The probability of A given B and C is the probability of A and B and C divided by what you're conditioning on, which is B and C here. And then we can just similarly break it apart. So probability of A and B given C multiplied by the probability of C. This is what the numerator means. And the denominator is just probability of B and C. And then similarly, this probability of B and C can be broken into the probability of B given C multiplied by the probability of C. It could also be expressed in this other way too, but it's not helpful here. It could be expressed as probability of C given B times probability of B, but that's not helpful here. There are two ways of writing it. Either you can write probability of B and C as probability of B given C multiplied by the probability of C, or as the probability of C given B multiplied by the probability of B. But that's not helpful here, so we just focus on this. Then we can slash and thrash out the common parts. So we notice in the numerator that we have this PC here that crosses out. And similarly, this part crosses out here. So we're just left with probability of A given C. So the probability of A given B and C is just equal to the probability of A given C. That's awesome. So this idea of conditional independence is actually quite important in Bayesian networks, which are also known as graphical models. So Bayesian networks, apart from graphical models, they could also be called Bayesian belief networks, decision networks, causal networks, Bayesian model, and even probabilistic directed acyclic graphical model. So they have quite a lot of names here. In fact, this is a Bayesian network for COVID-19 or a condition with similar symptoms here. We can look at the symptoms, background risk factors, infection possibilities, and there's even a legend here. So these are indeed widespread, and they use conditional independence. That is a key part of Bayesian networks, which we'll talk about in other videos. So idea is that in Bayesian networks, so they can be called many different names. Each edge is a conditional dependency here. So each of these edges, so we can see this rain node, sprinkler node, and grass wet. And I talk about this more in other videos here, but these are what nodes are here. So each node is a distinct random variable. So rain is a random variable, sprinkler is a random variable, grass is a random variable, and here similar, grass wet is similar to A, B, and C in our example. These are just like Booleans. It can be true or false for their values here. So grass wet. For grass wet, its parents are sprinkler and rain. And for rain, it doesn't have any parents here. Sprinkler's parent is rain. So given the parents for each node, each child node is conditionally independent of its non-descendants, its non-children. So essentially what that means is that grass wet is conditionally independent of rain, which is a non-descendant, actually its parent, given sprinkler. So grass wet here is conditionally independent of rain, given sprinkler. That's what it means here. And I will go over this in other videos, though, how to interpret these networks. But that's what we can say. So grass wet is conditionally independent of rain given sprinkler. And just as we had seen here, we can then derive that the probability of grass wet given sprinkler and rain is equal to the probability of grass wet given sprinkler. And the key idea again in this example is that, grass can be wet due to sprinklers or to the rain here, for instance, and then the rain could also impact the sprinkler system as well. And all of these are connected here in some way in a Bayesian network. So this is sort of how you can see some probabilities here. So the probability of, grass being wet is conditionally independent of rain given sprinkler as well. So we can see these probabilities play out here, which are a key part of Bayesian networks. In fact, Bayesian networks greatly benefit thanks to conditional independence, of the node given its parent. We can ultimately break apart these probabilities as is, where the children nodes are just dependent on their parent nodes. And so we can come up with a graph structured approximation. And it just shows that conditional independence is super important and super helpful, especially for probabilities in these networks. But I'll be talking about this more in other videos. I just sort of wanted to motivate why this is important stuff that we're doing here.